Donc, bonjour tout le monde. La présentation ça sera en français. Je voulais seulement faire un petit introduction en français. Je dis en français? Non, ça sera en anglais. Je voulais dire des petites choses en français seulement pour commencer. Je vais vous parler aujourd'hui de parallélisation massive des algorithmes de branchement. C'est avec la supervision de mon professeur Manuel Lafont au département d'informatique. Donc, pour commencer, let's make the switch to English now. Thank you very much, everybody, for coming today, for attending to this presentation. Let me just begin. Let me introduce you now the outline that I'm going to present for the following 45 minutes. First, I'm going to just start with a little introduction of this project, the ideas, and what is the objective that we're trying to solve. And then going to present some applications that we hope to solve with this project. And then I'm going to present just a little introduction or just a brief description of what a branching algorithm is, just to have a visual idea of what I'm going to be showing during the whole presentation. Then, after all this, I'm going to talk about the load balancing strategies that we must include. Everything is going to be explained along the presentation, and just in case for any doubt. And of course, all the work that has been done in the past and recently. And after this, I'm going to present to you my contribution to science for now, which is a novel load balancing strategy. And then I'm going to present the results using this novel load balancing strategy compared to other strategies previously mentioned. And after that, I'm just going to show some tools that are still in development. I just wanted to share this little quote, a parallelism, about in Spanish. Then a little introduction for this. For this whole project, the high-performance computing is targeting to take advantage of all multiprocessors machines. And our idea is that when we have just any simple algorithm in general, all the time we use just a single processor. But if we have a supercomputer at home or maybe in our office, we would like to take advantage of all the power that as much as possible. Our motivation for this is that most algorithms or several problems require exponential time solutions and of course also exact solution. And this kind of problem do not scale very well for large data sets most of the time. One of these examples in bioinformatics would be like clustering genes and proteins, finding consensus DNA and sequences. Other more commonly known examples would be like finding the optimal delivery routes, detecting communities in social networks like Twitter and Facebook. The objective of our project in this case is to create a fully generic library in C++ to massively parallelize any sequential branching algorithm. And in order to contribute more than just doing this library, I will present a novel load balancing strategy. And of course, after all this, one of the main objectives as well is that any user without even a knowledge in parallelism is capable of just applying parallelism just using this library with just some little modification to the code. That is pretty simple, even more simple than OpenMP. One of the applications in bioinformatics is to find exact solutions with this branching algorithm, this algorithm usually take exponential time. One of the examples as previously mentioned would be like cluster editing for grouping genes in functional classes and gene order-based ancestral in phylogenomic reconstruction. To put this into summarize or just to give a little bit more of clarity, I'm just presenting you today this cluster editing problem. This is very brief. Just for example, giving a graph G with vertices D and edges E. and a non-negative integer k, we would like to answer the question, can we transform this graph by inserting or deleting at most k edges into a graph consisting of a disjoint union of clicks? But first, what is a click? A click would be this, what we just I'm showing you today in this little drawing here. A click is a graph where all the vertices are interconnected between each other. That is, just each vertex has an edge to any of the other vertices. Then this would be an example of this problem. This would be like our graph. In the practice, vertices represent genes. The edges would represent similarity. And then after solving this, we would have something like this. And then each particular click will represent those genes that are in charge of the same function in an organism. Where k, in this case, after solving this algorithm, we would find that we would happen to delete 6 edges and insert 3 more, which k was the minimum number of changes. And then how is that solved? If we try to visualize our algorithm, then having a P3, before that, a graph is a disjoint union of clicks if and only if it has no P3. And a P3 is the smallest graph that we can find out there that is not a click. And we would like to transform it into a click. And having a big graph, then we can just applying this strategy, we can just transform our big graph that we had initially into a disjoint union of clicks. Then one way to do it is, if we try to transform this into a click, it is deleting one edge that we have here on the right, and then we will have 2 clicks. Or one click in here and one click in here. A single vertex is also considered a click. And then the other way to branch or to find another possibility or pathway would be just deleting the other edge. But another, the remaining possibility would be just inserting the missing edge between U and W, as we see here. Then we will have the 3 possible pathway to explore our algorithm. That would give us a complexity of big O star 3 power k, where star stands for any component that is not exponential time, and 3 power k, where k it would be the possibilities, the branching possibilities. In this case would be 3, and k would be our parameter of interest. Then just to summarize what a branching algorithm is. It's any algorithm that explores 2 or more different choices, as we just as I just presented. Then these algorithms are aimed to find exact solutions, unfortunately they are exponential, and we have to deal with it. The complexity of this, to generalize it, would be the same big O star of C power k, where C represents the branching possibilities, and k is the parameter of interest, as I mentioned before, which is usually also the optimal solution that we are trying to solve. These algorithms are aimed also to solve NP problem, NP complete problem, exactly. So as the previous example, other common known problem is the minimum vertex cover problem, or the traveling salesman's problem, or consensus DNA sequence. Just to visualize a pseudo algorithm, branching pseudo algorithm would be like this. We have one particular function, which is the way that we define it on computers. We will have some termination condition, and then we will have our branching possibilities like this. Then this would be a complexity of 3 power k. So it's 3 power k. Well, to summarize of this which is I would like to highlight this because it is really important for the whole project, because generalizing, we have 2 types of algorithms, and those algorithms are essentially defined as functions in programming. And these 2 types are those who return a value and those who don't return a value, which is also called as a non-weighting function is those ones who do not return a value. And the weighting function are those who actually return a value. Visualize it, this would be the non-weighting version. The first one I just presented 2 slides ago. This one. And then the weighting version or returning version would be this one. That every call in the recursion, it is actually returning a particular value. That is because we, depending on the algorithm, we might have to compare, to merge, or just choosing the minimum or the maximum, depending the user criteria, and also the algorithm. Then one of the challenges of this is how do we actually parallelize, or how do we make calls in parallel to each one of these branches? If this is recursive and the code, it only takes maybe, for this case, only just 9 lines. And what the most important thing is trying to make parallel calls for each of these branches. And that is a non-trivial task, because assigning a branch to a particular processor, it is difficult, and also we have to think, we have to distribute it well. During the presentation, I will just show some examples about this. And this is also not embarrassingly parallel, which is not, which means that it is not as simple as parallelizing a simple for loop. Then let me just introduce you to what load balancing is. When we're just talking about parallelism implemented for recursive algorithm, we have to think about the workload of the processors, that which is important because most of the time with a recursive algorithm or branching algorithm, each particular branch along the whole exploration tree might have a different complexity. One of those, or several, or sometimes most of them, just return in a few fraction of seconds, and at some point, in some other cases, just a single branch is the one. It is one of them who is the longest and more difficult to solve. In the past, have been proposed several strategies. Today, I'm just going to present you 5. Even some of them that I'm going to present you today are just a mix, just a combination of others in here, either just improvement of the previous one. But before just trying to present you this, I'm just going to clarify, or just to make visualize how would be the exploration of a sequential branching algorithm. We define left as the first call in our branching algorithm, and right as the very last call in our algorithm in the same scope. And this would be like the exploration sequentially, this animation. If you don't see it, just let me know, please, and I will just do something. This would be the example. The broken lines just represent those branches that are going to be solved after the working branch, which is the solid line. And the triangle just represents the rest of the exploration tree, just for the purposes of this presentation. And this would be just the end of the exploration of the algorithm. And after they return any value, or everything is sequential, when they return everything, finally we're just going to find our solution. To continue, then let me introduce you to what load balancing is. First, as I previously mentioned, we would like to distribute the load, or the tasks that we will just be obtaining over the exploration tree. And then we would like to assign maybe a branch, or just even if it's not exactly a branch, but we would like to, in principle, it is assigning a branch to a particular processor. And this is strategy proposed by Bokhari in 1979. We can find it out there in the literature as a static load balancing. It's the easiest one to implement, and I'm going to show you in the next slide why. And one of the other advantages is that the P probable heaviest branches are solved in parallel, where P is the number of processors that we have available. One of the disadvantages of this is that we usually get insignificant speedups. Everything is clear with this figure here, just imagine that we have this exploration tree, and then logarithm base 2 of p, where p is number of processors again, and this imagine that we have an example with 8 processors. Then at depth 3, which would be the logarithm base 2 of 8, we will assign each branch to each processor. Then in this case would be 1 processor and 1 branch with 8 processors. But the problem with this is that, as I previously mentioned, most of the time those branches just take a few fractions of seconds to solve. And then we end up with just a single processor working with one of the heaviest branches. And these processors, after returning, they don't do anything else. They just go to the bench and then they stay there. That's one of the problems, because as I mentioned, if the other processor, the other 7 processor takes only just a fraction of a second, then that means that the whole execution was on this branch, and we're not actually getting any improvement at all, even though it is parallel. This is just a way to animate it, to see how it actually works, where the red arrow represents a parallel call. Then, as we see here, we are just making the parallel call. Imagine that we have only 4 processors. Then after some time, they return, and we end up with one of those big branches and really difficult to solve. And they don't actually go here to help, they just return. And that would be this static load balancing. And I'm going to talk about this author, Wira Piresh, of 2011, in a few slides. But they presented, in order to present their idea, they also compare with this static load balancing, and they demonstrated that we don't usually get relevance improvement with this, basically almost nothing at all. Where the red bar represents sequential solution, this is execution time in seconds. The blue one represents the parallel solution. As we see here, we don't get actually any solution with any speed up at all. So except for this, but also that since this is the exploration, usually the exploration of a branching algorithm, it is random, and then they probably just get lucky. And also they actually say that we just somehow depend on luck when exploring this kind of algorithm. The idea is just try to set apart the luck and trying to solve it as soon as possible. And we have the next strategy, which is the randomized work stealing approach. This strategy is really efficient. Nevertheless, it has its little problems. It was presented by Xu in 1989. And one of the advantages is that processors get assigned a new task by other processors as soon as these processors get idle. It means when they sit on the bench, there will be another processor aware of that and going to assign a new task. One of the disadvantages of this is that the idle time is an issue for the weighted algorithm. That is, for the weighted algorithm, the returning one, those 3 algorithms that return a value, we will have to wait for the result of each branching call in order to do a merging or a comparison or anything else. And then after, if we do that, that means that a processor might just end up in line with 2 or 3 more processors. That I'm going to show this in a few more slides and how it's actually happening. And those are basically the disadvantages of this. Also, something to highlight that for now it is not good nor bad. It is that this is a decentralized topology, meaning that processors don't have to communicate to one master or center processor to request for task, because any processor will assign a new task to any available processor. This would be the way that it's actually working, this animation. Since it's random, actually, this would be, for example, for 3 processors. We make a parallel call from the left to the middle, and then we go sequentially to the right. And then we have 2 pending branches in here, and then we just keep exploring. And now this one just finished, and then this processor in here was able to make a parallel call to the left in here, and then continue the right sequential as we see here. And then this one was also able to perform a parallel call here, and then continue to the right sequentially, as we see here, sequential. And then this will have a pending branch. Now, I wanted to show you this particular part of this animation. This processor is already waiting for the result of this processor. And also this processor is waiting for the result of this processor. Probably, who knows, this branch is the longest one. If we have three processors working on this branching, that means that right now we are only using 30% of the capacity of our machine, because these two are just waiting there, and they are not able to go here to help it, because they cannot leave the scope without just doing the comparison, for example, for those weighting algorithms. This is not a problem for the non-weighting algorithm, because they don't have to wait for a result. And then everything will just return is here. And this distribution of the processor, it is randomly. Then that means, for now, I'm just showing you the right branch, but that also means that this is happening in any other branch or any subtree in this algorithm. Then we have the next balancing approach presented by Abu Kazam and the other contributors in 2006. It is called, or we can find it as a hybrid approach. The advantages, basically, since this is a combination of the two previous strategies, and also since it's a combination, somehow they share also the advantages and the disadvantages. They definitely share the same disadvantages. They share one of the advantages, which is the p-probable heaviest branches in parallel, because the closer we are to the root, the more probabilities of finding an optimal solution within a particular branch. But also, one of the hybrid approaches actually solving with this is that the first approach, where processors were returning, they were not helping the branch. And in the previous one, we are just distributing tasks randomly. That means that we probably will just not distributing tasks exactly for the first logarithm base 2 of p, where p is the number of processors. I'm going to explain this in everything is going to be more clear in this. It is this strategy. First, we apply the first strategy, the first load balancing, which is the static load balancing. We distribute a logarithm of p here, and then we just start solving. But for example, let's imagine that p1 returns. This now is available, and then the processors during the branching will be aware of any available processor somewhere. And then what it's going to do is going to prune one of the branches, and then it's going to send it to that available processor. Here, the pruning is giving us warranty of not solving this branch twice or more. And this is the strategy. Another strategy that we have is the task queuing approach. It has some differences. The advantages is that it's aimed to decrease this idle time. The disadvantages is that it is difficult to define in queuing criteria, and the queue must be fixed, the size, and some of the heaviest branches will be eventually skipped. It's going to be really clarified in the animation, the following slides. And this has a central topology, meaning that all processors must communicate with the center node or center processor or manager for tasks. Then when they go to the bench, they sit there to waiting, then they will have to request to a manager, and then the manager will just be in charge of the communication for just distributing the tasks. This would be what they did in 2006. They created a driver within the broken line, the broken square. The driver is in charge of splitting this the whole expression of the algorithm, and then it's in charge of creating a job queue. Then what is happening in here is that since now there is a job queue, when a processor, any processor that is available, then the driver is going to queue the first task in the job queue, and then going to assign it to one processor. And then the processor will just continue branching on that task. But this has a little inconvenience, as I previously mentioned, is that this is queuing criteria. It is difficult to handle because somehow we have to predict if the task that we are in queuing is promising or not. And this is not something that can be really generic for any algorithm. It is something quite specific. It is possible to predict with some algorithms, but it's not applicable. Exactly the same criteria wouldn't be possible to apply to any other algorithm. And of course, one of the problems with this is the queue size must be fixed, because as we know, this is an exponential time algorithm. That means that if we enqueue tasks to the job queue, also this queue would grow exponentially, which is would represent a memory leak, and then this is definitely must be handled. That's why the reason it has to be fixed, and then we have the problem of the criteria for enqueuing. One of the other the other problem is that since let's imagine that the job queue has a size of 10. At some point, a processor is just exploring the tree, and it realizes that that it cannot enqueue any more tasks. What it's going to do is that processor is going to go deeper and deeper within the search tree, and then when there is an available where there is room available in the queue, then it will be able to enqueue more tasks into the queue. But the problem with this is that it will be really deep down in the search tree. Now, it could have probably just gone 10 or more. Who knows? Actually, that is not a specific number for that. But it would have been skipped too many branches that are actually more shallow than the others. And that the idea is trying to solve the shallower branches as possible. Then we have the other scheduler. It is called a scheduler-based approach, presented by Weir-Presch in 2011. The advantage of this is that it's aimed to decrease also the idle time, the same as the previous one, but in this case they do not use any queue. So we don't have, in this particular scenario, we don't have the problem of trying to define a criteria to enqueue, nor we have to control the size of the queue, because well, there is no uses of any queue. One of the disadvantages is the same as the previous one, because some of the branches will be eventually skipped. And then this was specifically applied for the minimum vertex cover. So this strategy, it is aimed to solve those algorithms where we can just predict that a single branch is going to be the heaviest one. Just what it is pretty common for the vertex cover due to the nature of this problem, but it wouldn't be applicable to any other algorithm. Then it is not entirely generic. And this has a centralized topology as well, meaning that all processors will have to communicate with the scheduler for getting jobs. Then this animation, the donor represents a processor who is in charge of giving tasks to the other processors. And then the second one represents any processor that is working, the one with the thread inside. And the blank square represents a processor that is requesting. For this example, we will have 3 processors. And then for this example, again, just since it is applicable, it was applied for the vertex cover. Here we are actually branching, going sequentially somehow to the left, and then making parallel calls to the right, as we see here. Then at this point, sorry about that. At this point, we see here there was no available processor, and then what it had to do is that it just went sequentially to the left, and now there is a pending branch. Now this processor finished, and now is requesting a task. Now now we have a communication within this processor and the scheduler, and the scheduler now communicates to the donor, which is the one solving the very left branch, and now this processor now is going to give a task to this processor, just like this. But still, we see that there is this pending branch. But as this branch is actually shallower than this branch, it is likely to have a better solution than this one. And everything is going to just keep working the same way, and then they will just return. And after all of them have returned, there will going to be a termination signal, and that's it. As we see, with these ideas, let me just introduce my contribution to solve the weaknesses of the previous strategies, because we have still room for improvement. And some little highlights before continuing is that I fully developed a generic library in C++ that is capable of solving any branching algorithm that is initially sequential. We have now several strategies, load balancing strategies. By default, we are using the randomized work stealing approach. It was the second one that I mentioned. It is that we know that it is really efficient, but it has its weaknesses. And the idea with this novel load balancing strategy is that it's more efficient. It is aimed to solve the shallow branches that will contain that are likely to contain a better and a most optimal solution. It is developed with a decentralized combined with a semi-decentralized topology to relieve the communication overhead. This topology will be explained in a few more slides. And of course, with this novel dynamic load balancing, we are reducing the idle time. And all branches, since the default strategy is random, that means also that all branches are likely to be assisted equally. This would be the animation of the contribution, the novel dynamic load balancing. We are aiming to solve the shallower branches. As we see here, now we have two branches. This is basically the same animation. So far, it is the same as the work stealing approach. But now we see that this processor realized that there is an available processor somewhere. What it's going to do, instead of just making a parallel call to the left, is actually making a parallel call to this pending branching. And then it was just going again. Now, it goes sequentially to the left because all the other processors are working. But now, at some point, this one will just return, will just finish its task, and now will be available. What is going to happen is that this processor or any other processor, well, it's going to be this processor because each processor is in charge of its branch. And then it's going to just make a parallel call for this pending branch. And this is going to be repeated all the way down, always solving most difficult branches. This is not limited for only this right branch. Since this is random, this is actually something that is going to be happening within each particular branch. Then this branch will just perform exactly the same strategy as here, because this processor, the processor who took this branch, will be in charge of making parallel calls as well within this branch, the same way that this branch is doing it. And this, what is actually doing this is that since we are making parallel calls for those branches who are more difficult, that means that those processors won't go that often to the bench just to be there waiting for results. Also, since we are pushing shallower branches, that means when we have this problem for one processor waiting for the result of the other, and then the other and the other, that means that we are reducing how many times we are actually facing this kind of issue. Then also that represents a decrease in the idle time, and if the idle time is decreased, the performance is improved. Okay, just to summarize, let me just start presenting some of the preliminary results of this. To test this project, we tested it using the minimum vertex cover, which is one of those problems which is really known and we have data to compare with. And then also we tried the algorithm, the project, the library with the two versions of the minimum vertex cover problem. One, just using a non-weighting version, which works like this. I'm not going very well in details, but the basic idea of this is that we have a binary exploration, binary search tree, and when they reach a termination condition, what it's going to do, they're going to compare the result with a global variable, and then if it's actually promising, if this is better, it's going to swap it, and that's what it's going to do. The weighting version is doing something different. When it reaches this terminal condition, what it's going to do is going to return the actual result. And then this scope is going to be in charge of comparing the two results, which then is returning the cover with the minimum size. And in order to do that, we created pseudo-randomly 100 graph size 600 with the density of vertices of edges of 4 over n. We tested this on Compute Canada Beluga, where each node was containing 40 cores. And this is the reference of the CPU, just in case somebody is interested in. A node in a supercluster or supermachine is actually just a computer interconnected with, well, just to summarize, a cluster is just a big network of powerful computers interconnected by network. Then they are called, each one of those powerful computers is called node. That's just a comparison using the randomized work stealing approach. There is no novelty in this graph. What we have here is just a comparison between the two algorithms, just to show that the parallelism is that one of the algorithms is getting more benefit of the parallelism. Here, the weighting versions, those who return value, are getting more benefit than the non-weighting version. But also that's because the non-weighting version of the algorithm, it is already really efficient. Here, just looking at 40 cores, 40 processors, we see that the light blue, that we get up to more or less 31 times faster compared to the sequential version. But using the weighting version, which is not that optimal, but since this is a comparison between its sequential version, we get more benefit in here. It's almost up to 27 times faster. And just showing the actual result for the novel dynamic load balancing strategy, just after an analysis, using, for now, this is for the weighting algorithm, those who actually need to return a value. We see, of course, the more the processors you the more the single time for each one of them that they will be just sitting on the bench. And we have to sum up this single time for each one of them. And that also means that it is quite linear, but it is increasing the more processor we use. And this is a problem because we're not actually using 100% of our machine, of the power of the machine. Then we see here that on just consider on the left axis for now, the idle time for a default in parallel solution for this branch algorithm, we see that we get more than 50% of the total execution time is just idle. They're just sitting in the bench waiting result for another processor or just waiting for another processor to assign a new task. After applying the novel dynamic load balancing, we see an improvement of more than 50%, just steering at the right axis, that the idle time was decreased. Of course, this also represents a big contribution for the actual performance, which is in this graph. We see that after the ideal represents, I'm not sure if that's percent. The ideal represents the optimal optimization that we can get after parallelizing. Then that means if we use 10 processors, we would expect to get 10 times faster in the solution, and so on and so forth. And then we see that the default, by default, we using just 40 cores as a reference, we get a speed up to 27 times faster. But after applying the dynamic load balancing strategy, remember that we just reduced the idle time more than 50%. We speed it up more than up to 49 times faster, even just going above the ideal, which is also commonly known as superlinear. Then just applying the same ideas, but for the non-weighting algorithm, those who do not return and they swap the result at the very end. They don't. This algorithm doesn't face the problem that where a processor is waiting for the result of the other, because they don't have to wait for anything. But then the idle time is just defined, but that time that they are just on the bench waiting for another processor to assign a new task. It is quite insignificant because we see on the left axis that it is barely 3%, but of course we can see again that the more the processors we use, the more the idle time it is. But 3% might not be that significant as we see it like this, but of course we have to remember that this is a exponential time algorithm, which means that this is the time that we must consider, and each particular millisecond that we add to an exponential idle time might be really significant in the total execution time. After applying the dynamic load balancing strategy, we see that we get an improvement of up to 100%, just staring on the right side. It was reduced almost to zero. It is not zero, but it's very close to zero. Comparing one another, we get an improvement of almost 100%. Then this is actually tackling the problem that the other strategies had before, because since the one with the queue in the queuing strategy was aimed to avoid these processors to be on the bench just waiting for a task, but using this strategy they are not that often on the bench, and this is why we're getting that much improvement. It is like if we were using a queue without using a queue. Then the actual performance of this, we see that this, comparing again with the default using 40 cores in reference, we get a speed up of up to 31 times faster. And after applying the dynamic load balancing strategy, we improve that up to 38 times faster. Very close to the ideal. But again, just to remember, this algorithm is already quite very efficient, and now we are actually doing it more efficiently. And these were the results. And what is actually in development right now is this. We have the supercomputer escalation. In order to establish communication between nodes, previously explained for a supercluster, we implement the message passes interface, which is commonly known as MPI, and the semi-centralized topology internode and the centralized approach intranode. That this is actually very well explained in this figure. We imagine that we wanted to apply this library to just your computer at home. Everything is going to be run within this broken line, and those processors will assign tasks to the other processor as soon as there is a task, and of course if there is an available processor. But if we are going to use this in a supercomputer, everything is going to be executed initially by the center node. The center node is going to send the input data, or a seed as we call it in here, to the node number 1 as convention. all the nodes will be just aware of any other node. And then when this node run out of processors because they don't get busy and it still needs help, it will just request help to the center node. And this is what we're calling semi-centralized, because the center node is just returning true or false. It is not actually, we don't have to send data to the center node and then the center node is sending it to one node K. What it's doing is that we're just returning a signal, a true or false signal. If it's true, we are returning the ID of the available node. And then this node will be in charge of sending the task to a particular node. If it's false, you would be probably wondering, but why would it be false? If these nodes, all the nodes are aware of the availability of any other nodes. That's because a communication between within the network, because there is no shared memory. The memory of this is totally different than the memory in node K. That everything must be sent by the network. There is always a tiny delay. Then there is a chance that when this node was aware that there was an available node somewhere, and then requested help. Then by the time this was requesting help, the center node was actually assigning the last task to the last available node. And now the center node is going to reply with a false because there is no longer that available node. And this one then won't just perform that parallel call anymore. But of course, at the same time, this center node is in charge of broadcasting that information to all the other nodes. Then we are just decreasing the time that we request tasks to the center node. That's why we call it semi-centralized. Some of the references, just in case somebody wants to rate a little bit more about it. I would like to thank Professor Manuel Lafont for acting as my supervisor in this research and guiding me for finding good knowledge about it. Thank you everybody for your attention. If you have any questions.
Thank you very much, Andres. It was interesting. Do we have questions from the participants? Well, I can start with one question. So you said you were developing a library. Is it already available?
Would you repeat it, please? Your communication was a little bit broken.
So your main objective is the development of the library to speed up the parallelization for
yes,
branching algorithms. So I was asking, is your library, your implementation already available somewhere?
It is already available on GitHub, but it is on a private Git for now because I'm still developing. Mm-hmm. But if anybody is interested in just taking a look, you're free to contact me, and I will be happy to give you the guide and a copy of this library. It will be eventually public.
Okay, thank you. So the second question is, I've seen that you have applied it mainly for graph problems, for problems on graphs, okay? Do you plan on applying it on other types of problem? For instance, these are also graphs, but you have a lot of problems related to the distribution of information.
Yes, actually, that's the purpose of the library. It is aimed to be applicable to any algorithm. It doesn't have to be for graphs. Then it is not limited only for graphs. Any branching algorithm, whether we want to use even the merge sort, we have also tested it for merge sort. Also, it is being tested for Fibonacci and other any other branching algorithm. It is fully generic.
Okay. And so what are the next steps that you want to implement? What are the improvement that you see that can be brought to your work, actually?
That is in development. Well, what is in development for now is that for now it is ready to what we have in this figure. I'm not sure if you are still seeing. Yeah. What we have within the broken circle, everything is already done. But the communication between node for the supercomputers. It is still in development. I hope to develop within the next 3 weeks because it's almost ready. It is just because when we have to send data between nodes, we have to serialize and just send it as bytes. And this is not as simple as Java that we just convert anything to bytes. In here, we have to do it somehow manually. But that's what I'm still developing. I hope to finish that. And after doing that, the library would be totally finished.
Okay, thank you. So for now, I'm finished with my question. Do we have other questions? You can just open your mic or raise your hand as you like. We still have 2 minutes. Well,
okay. Sorry. If no one's asking, I do have a question, but quickly. So you said that sometimes you can achieve a running time that is better than a linear speed up. I mean, how can you achieve better than linear, a speed up higher than P with P processors? That seems contradictory. So do you have an idea of why?
Yes. Well, actually, there might be several reasons. For this example, it is because I was comparing one strategy versus the other. And but in general, for the branching algorithm, that's because let's imagine that we are trying to find the shortest path over a labyrinth. The way to know is that if we are lucky and we choose the shortest path immediately, we might probably solve it in just 5 seconds. But if we solve, if the shortest path is the very end, the very last one, then we will have to go over all the possibilities, and probably all the possibilities will take, let's say, 60 seconds. If we use 2 processors, we would probably split that to 30 seconds. But if we use enough processors for that, and finally one of those processors grab the shortest path, that means that that processor will find the answer in 5 seconds only, even though the average it is a little bit more than that. And since most of the time these algorithms are bounded, that means that they are communicating between all the processors, and then when an optimal solution is found, there is no need to keep exploring all the branches. Was that clear?
Clear for me, thank you.
well, are there other questions? Or if you don't have question now, you can still write to Andres later with the question. So you showed your email address, right?
Yes, it's here.
Yeah.
I'm going to just write it down again on the chat room. Don't be afraid of asking me. The idea of this library is that even though you don't know or you don't have any knowledge at all of parallelism, this is aimed for those who actually don't even need to learn about parallelism.
Perfect. So, well, then we thank you again, Andres, for your presentation. Very interesting presentation. And so I will see the participant next week for the next Club Informatique. Thank you very much.
Thank you.